Hi, myself Mohit Agarwal, and I am here to present you about music recommendation system. So, recommendation system. Basically, every industry in today generation relies on recommendation system. For example, Amazon, e-commerce industry, is totally dependent on recommendation system. Like in today's generation, in today's world, no one has sufficient amount of time. So we need to have sufficient amount of knowledge in a particular time period. So that they can track that and they can actually get the right piece of information with us and they can actually deal with our companies or they can actually trust our companies. So suppose is same is the case with Amazon. The basically recommendation system is a simple model. Suppose X person likes apple and mango and Y person likes mango and grapes. So we would give suggestions to the X person for the grapes, and we would also give suggestion for Y to the Y person for apple. So this is a simple recommendation system. This is a simple model of the recommendation system. So it's all actually evolved from the user's choice and preferences. Now, here is the challenge. There are 20 million songs in the market, and how we can recommend each music to the users. So here are the different albums shown here. You can check out the albums. So different music albums are shown. So this is a challenge supposed to be. Now, there are different recommendation features like discover radio related artist now playing. Like suppose X person likes particular singer songs, Y person like different genre of songs, different genre of song, different artist songs, different movie songs. So this all the features which actually helps us to build a rating matrix. That's the user's feedback, and according to that we can judge and we can build a good recommendation system model. Now, how can we find good recommendations? So there are certain features we need to know about: manual curation, manually tag attributes, audio content, metadata, text analysis. And text analysis is one of the very innovation method in which we can do sentimental analysis and we can classify the words into different sections like positive, negative, and neutral. So it's also a very good method. And lastly, and the most important is collaborative filtering method on which our theorem is based on. It's collaborative filtering. It's a very good method and it's a very easy method to build a recommendation system model. Now, collaborative filtering. You can see here the Netflix guy who has made Netflix has created a recommendation system is like 2009. So how he had created and the price you can see the price value actually the how much the importance is of recommendation system model that the Netflix guy has made, and now everyone is relies on after 8 to 10 years everyone relies on recommendation system. So it has a lot of future scopes and it's very huge demand in today's market. So here is example of collaborative filtering. Like I have given the example of apple, mango, and grapes. So here is an example of PQRS. So suppose a one person likes PQRS and second person like tracks of QRST. So we should recommend track P to first person and we should recommend track T. We should recommend track P to second person and track T to first person. So it's actually the recommended system model working, how it works and how it goes on. Now here is explicit matrix factorization. According this is the mathematical part of the recommendation system that how the recommendation system in backend it's working. Like a users explicitly rate a subset of the movie catalog. Like every users have a different opinion, so differently they rate they rate the movies, and the goal is to predict the how users will rate new movies. So we'll create a rating matrix according to this, and according to this we will build a new matrix model through which recommendation system can be built. So you can see here how the recommendation system metrics are made, how the users give the choices. Approximate rating matrix by the product of low dimensional users and the movie matrix. Says minimize RMSE. RMSE is a root mean squared area error criteria through which the different models are built. So these are mathematical expressions through which the method is made. These are all the formulas for the rating the different movies and knowing the regulation. Lambda is here the regulation parameter through which we can control the error part. Bias is the term used for error part, and the latent factor vector is used for XU. This is user's latent vector, and so here it goes on. Now we can go with the implicit matrix factorization. Replace stream counts with binary labels -1 equal to streamed and 0 equal to never streamed. Like we can calculate, we can actually divide into two fact. Our predictor variables can be divided into two factors, 1 and 0. 1 means trimmed, 0 means never trimmed. To have a easy chance of classification, we can build a classification algorithm here. So we can minimize the weighted root mean square error criteria using a function of stream counts, and as weights we can calculate them as a weights. You can see here the matrices model and the formula for it. The different formula goes for it. So now the alternating least squares method. We can first initialize users and item vectors to random noise. First we can actually create the model to the random noise method, and we can create them as a factors. Then we'll fix the item vectors and solve them for optimal user vectors. Then we need to take the derivative of loss function with respect to users vector, which is equal to 0. Then we need to solve the resultant system of linear equations model for the matrices. Now we'll fix the users vector and solve for optimal item vectors, and we will repeat until convergence method. Now alternating least square methods, that y transpose equal to c union equal into y equal to y transpose into y plus y transpose into C union minus identity matrix into Y. So basically, it's all the mathematical stuffs which is actually generated in the backend. We don't need to check this stuffs and all. We just have a scroll down to have a look of a glimpse of it. There's a sparse metric operation and everything. It's all the mathematical part. It doesn't need to. This is a sample program of a alternating least squares method implementation in the recommendation system model. You can have a look on this. Now, how can we use the learned vectors? User item score is the dot product method actually. So PU we can use for that user item score, and A transpose into BI. So item similarity is based on basically cosine similarity. We have a formula for that. BI transpose into BJ by modulus of BI and modulus into modulus of BJ. Both operations have trivially complexity based on the number of the latent factors, that is denoted by O to the function of F. And now we can look the latent factor vectorization in two dimension, but how it actually looks, it's a visualization part, but how the latent factor might look. Like here we have divided the five into five musical sections: hip hop, reggae, jazz, metal, classical. So you can have a look on it, at how it looks basically. So different numbers, different colors are denoted for different music albums. So now we can have implicit matrix factorizations model, that how it actually proceeds in the backhand. The first is the item vectors modulus L equal to 0 is the one case, and the modulus L equal to 1 is the one case, because we have divided the target variable into two factors, 1 and 0. You can have a look on this. So it's a simple backend model. Now you can have the one map task, that how in the Hadoop it's actually distributed, the how it's actually translates into Hadoop, big data Hadoop. So lastly, now from the implicit matrix factorization with Spark, how it actually manipulates with Spark. There are several operations you need to do with Spark. So these are the models. You can have a look on it. Now we will try an algorithm approximately nearest neighbors algorithm, that is k-means or k-nearest KNN algorithm will be used to actually generate a good rating matrix and to have a glimpse of it. So this is the ensemble model of the latent factor. Ensemble means nothing, just to grouping the model. It actually segregates different weak learners model into the strong learners. So you can see here there are different models from 1 to n, and we can ensemble them and make a strong model. So basically it develops a very good model. It's nice part of this. And several problems which we can actually occur after building this recommendation system, that how we can go through a predictive model to related artist, how we can learn from users feedback, how we can deal with the observation bias in the user feedback, how to factor the temporal information, how to evaluate best model performance. So best model performance can be evaluated just to put different algorithms like random forest, k nearest algorithms, decision tree, and several other algorithms for classification. For regression also we can use. Basically classification is good for this, and we can see the model accuracy, and we can actually decide which model is the best model, and we can how to best train an example model, how much value in content based recommendation. These are all the several problems which actually rises when we try to build a recommendation system, but it's all the part and parcel of the model. It's actually through this we can build a good recommendation system model. And that's it. Thank you for this. Thank you for giving me opportunity to build something innovative that is actually going in the market, and I am able to be a part of it, and definitely be helpful to be a part of this, and very and definitely be to be honored to give you the practical and presentation on music recommendation system, because in today's world everyone is talking about recommendation system and using machine learning techniques and everything. So thank you once again. I hope I will be a helping hand in this, and I am presenting my all the codes and all the presentation parts to you, so you can have a look on it and check this for the betterment. So thank you. Thanks a lot.